Hello everyone, I am Debayantash and I am a PhD student at the Spark Lab, Purdue University, working with Professor Shreya Sen. Today I am going to present our work on killing the electromagnetic side channel leakage at its source. This work is a joint collaboration with Intel Labs. To provide security and confidentiality of data, several cryptographic algorithms have been designed which are mathematically secure. However, these algorithms are implemented on a physical substrate which leak critical information in the form of correlated fluctuations in electromagnetic radiation, power consumption, or timing, leading to side channel attacks, allowing an attacker to extract the secret key. Here is the outline of today's presentation. First, we will start with the background of side channel attacks. Next, we will look into the motivation behind this work. Then, we will focus on the root cause analysis of the EM leakage from an integrated circuit. Next, we will move on to the design of the proposed countermeasure, which is known as Stellar, and finally, we will present our measurement results. Let us look into the basics of electromagnetic and power side channel analysis attacks. The power consumption and the electromagnetic radiations is proportional to the number of bit flips for each operation. For the attack, two types of models are commonly used: the Hamming weight and the Hamming distance model. The Hamming weight model counts the number of ones on the data bus for a particular operation, whereas the Hamming distance model is the number of bits changing from previous state to the present state on that data bus. The Hamming weight model is equivalent to the Hamming distance model only if the data registers are reset after each operation. The equation on the right shows that the power consumption depends on the number of switching events happening in the circuit. The Hamming weight model is a crude model and mostly works for many of the software crypto implementations, like in case of microcontrollers. On the other hand, the Hamming distance model is very useful for efficient hardware implementations, like in case of FPGAs or ASICs. Electromagnetic or power side channel analysis attacks can be non-profiled or profiled. Non-profiled attacks are the traditional attacks like correlational or differential EM or power analysis, and is a direct attack on the target device. On the other hand, profiling attacks involve a profiling phase and an attack phase, and is a more powerful attack. In this work, we mostly focus on the non-profiled attacks, although the analysis remains equally valid for profiled attacks as well. The attack modalities include chosen plaintext and known ciphertext attacks. The chosen plaintext attack is commonly used on the microcontrollers, while the known ciphertext attack is a more powerful and practical attack useful for efficient hardware implementations. In this work, we present the results with known ciphertext based attacks on AES-256 implemented in an ASIC. These are the steps to perform a correlational electromagnetic or power attack. It involves identifying the point of attack and choice of the attack model, Hamming weight or Hamming distance based on the platform for the attack. Next, for AES-128, for example, we guess the value of the key byte under attack and compute the Hamming weight or Hamming distance for each trace. Then, we obtain the correlation between the Hamming weight and the EM traces to recover the correct key. This slide shows how an electromagnetic side channel attack is performed. First, the EM traces are collected while the target device performs encryptions. Next, a Hamming weight or Hamming distance matrix is built for different key guesses. And finally, correlation is performed. As shown in the figure, the correct key emerges out after multiple traces are analyzed. Let us now look into the motivation of our work. Recently, it was shown that the AES-256 key could be broken non-invasively in just a few minutes using the electromagnetic side channels. The complexity of breaking AES-256 is reduced from 2 to the power 256 to 2 to the power 13. Transitioning from AES-128 to AES-256 only increases the side channel attack resistance by 2x. Most electromagnetic side channel attacks, as well as countermeasures, treat the EM emanation as a black box, without paying attention to the cause of the EM leakage. Many countermeasures have been proposed, such as data randomization using noise injection, electromagnetic shielding, masking, each of which has its own limitations. Hence, there is a need for low overhead countermeasure, which is generic to any crypto algorithm. To achieve a low overhead solution, we need to understand the root cause of the EM leakage from the crypto IC. Now, let us look into the root cause analysis of the EM radiation from an integrated circuit. We are all aware of the Maxwell's equations that govern the creation of the electric and magnetic fields due to the acceleration of electrons. This slide shows the genesis of the EM leakage in an IC. As the output of the digital gates switches its state, the acceleration of the electrons create changing electric fields, which in turn produces magnetic fields leading to EM radiation according to the Maxwell's equations. But what does the generated EM fields depend on? Well, it's the metal layers inside the IC carrying the current which act as dipole antennas and radiate. Now, these switching currents passing through the metal layers undergo a transformation to create electromagnetic radiation, and the magnitude of the fields depends on the dimensions of the metal layers. Higher level metals are thicker and has lower resonance frequency, and hence the EM leakage from these top metal layers has higher probability of detection using commercially available EM probes. The figure on the right shows the Intel 32nm metal-interconnect stack. We can see that as we move up the metal layers, the thickness increases, and at the bottom right we see that the top metal line along with the copper bump is huge compared to the lower metals. This slide shows the metal stack model in HFSS simulator. The far-field radiation pattern in HFSS is analogous to an infinitesimal dipole. This is a preliminary modeling to study the relative effects of the metal layers. A detailed modeling with an actual circuit layout is an ongoing study. This slide shows the E-field contribution of the individual metal layers for the Intel 32nm process node. At 1 GHz operating frequency, the detectable E-field for the state-of-the-art EM probes is 10 mV per meter. Hence, for the Intel 32nm process, metal layers M9 and above are vulnerable to EM side channel leakages. Hence, our goal is not to pass the correlated current through the high-level metal layers. But how can we really achieve that? The sensitive signals can be routed in the lower metals. However, power has to come from the off-chip components and hence needs to connect to the external pins through the higher metals. So, how can we restrict the correlated power signatures to the lower metal layers? We need to suppress the correlated signature in the lower metals before it reaches the top metal layers. Hence, we propose Stellar, which stands for Signature Attenuation Hardware with Lower Metal Routing. Now, let us move into the Stellar design. We know that MTD, or the minimum traces to disclosure, is proportional to the SNR square. Now, if we can embed the cryptographic engine within a signature attenuation hardware such that the current signature is significantly suppressed by a factor 80, then the MTD is increased by a factor of 80 square. With the Stellar technique, we propose routing the crypto engine locally within the lower level metal layers and then embedded within a signature attenuation hardware which significantly suppresses the critical signature even before it reaches the top metal layers. The attenuation can be achieved using an inline current domain signature attenuation hardware. This slide shows another view of the Stellar technique achieved through the white box modeling. This was first proposed at the host conference last year, where we received the Best Student Paper award. Now, let us see the design of the signature attenuation hardware. The goal is to have a supply current independent of the cryptocurrent. To achieve that, we utilize a current source on top of the AES core as shown here. The top current source stage provides a constant current, which is the average AES current, while the load capacitor accounts for the differences in the current. Now for a practical implementation, we cannot have the supply current to be the exact average cryptocurrent. Hence, we allow a delta margin which is drained away through a bypass path in the form of a bleed PMOS, which also provides negative feedback leading to DC regulation. Also, the switch mode controller loop is used to compensate for any pressure, voltage, or temperature variations and turns on the required number of current source slices to provide the average current. In steady state, the SMC loop remains disengaged and the attenuation depends on the load capacitance and the output impedance of the top current source. Now, before moving to the results, let us review how the Stellar technique is different from the current practices. In the leftmost figure, we see that even if the sensitive crypto signals are routed locally, the power has to be routed to the external pins through higher metals. Now for power SCA protection, as shown in the second figure, we can utilize the signature attenuation hardware to suppress the correlated signature. But if the routing is through the higher level metals, it would still radiate and would be vulnerable to electromagnetic side channel attacks. In Stellar, we propose embedding the crypto core within the signature attenuation hardware with lower level metal routing and then pass the attenuated signature to the higher metals. Let us now look into the measurement results. We designed a 65 nanometer test chip with both electromagnetic and power resilient AES-256 and subjected it through both time and frequency domain correlational attacks as well as leakage assessment. These measurement results were first presented at the ISSCC 2020 conference. We observed a greater than 350x signature attenuation leading to greater than 1 billion MTD for the protected AES implementation. Also, the test vector leakage assessment or TVLA revealed that the higher metals leak more compared to the signature attenuation hardware with lower metal routing. In comparison with the state-of-the-art countermeasures, the proposed Stellar technique achieves an 100x MTD improvement with comparable overheads. Hence, signature suppression along with the local lower metal routing allows to achieve a MTD of 1 billion compared to 10 million for the previous works. Finally, to summarize, this work provides the first white box model of the EM leakage through the ground-up root cause analysis. Stellar provides both power as well as electromagnetic side channel attack immunity through signature attenuation and local lower metal routing. It achieves a MTD of greater than 1 billion for both power and electromagnetic attacks, which is an 100x improvement over the previous works with comparable area and power overheads. It is also generic and can be extended to any crypto algorithm as a wrapper around it without any performance degradation. Thank you. Please let us know any questions that you may have.